All right. Let's calibrate the screen real quick. Let's see here. Okay. Let's see, where did we leave off last time? Started talking about lines. Okay.
Here's a points on line that grades t values.
So right, here we go. So we talked about how to find different points on that line by exactly what this young man said. You pick different t values, you'll get a different point on the line. Plugging in for the x, y, and z components. All right. So we kept talking about the vector v, right? The vector v. You had this picture here. You had a line L. You had some R naught, and you had some R. Then you had some V, which was parallel to L. And then you had some displacement vector right here between this point and this point. Let's call this P naught. Let's call this P. P naught P, displacement vector, was also called A. Then we discussed how A can just be a scalar multiple of V, since this and this is parallel. Then we said that, okay, let V assume some arbitrary A, B, C values. These values, A, B, and C, are called the direction numbers. So that's just kind of the direction numbers of L. That's just kind of some terminology. When we talk about A, B, and C, the components of this vector V, they're called the direction numbers of L. All right. And just so you know, you can have some other vector, let's say psi, who has components capital A, capital B, capital C, all right, where A is proportional to little a, B proportional to little b, C proportional to little c. This would also work, okay? This would also work as a vector that gives the direction of the line. Okay, so we attained in a set of equations, and rederive them. We attained that x is equal to x naught, or is it at minus at? No, x naught plus ta. Doesn't matter the order, but this needs to be a plus. Ta, y is equal to y naught plus tb. Z is equal to z naught plus a tc. All right. So this is a parametric equation for L because we have the parameter t. These are parametric. But we can eliminate the parameter t. We can eliminate it. And we do so by solving for t in each of the equations. So notice here, I get t is equal to x minus x naught divided by a. Over here, I get t is equal to y minus a y naught divided by b. And over here, I get T, you guessed it, is equal to Z minus Z naught divided by C. And notice T equals T equals T. So this equals that, which equals that. We have effectively eliminated the parameter, meaning we have represented this equation without the need of the parameter T. So this representation right there is typically called the symmetric, where this is the symmetric relationship. Symmetric equations, or a line. Those are the parametric, those are the symmetric. We have a vector equation for a line, and we have a parametric equation for a line. Okay? Your book wants you to know that A, B, and C are not necessarily non-zero. We can, for instance, have situations where A, B, and C assume the value, really any value, they can actually equal zero. Notice that they can't equal zero if you have it under this formulation. But before we had x is equal to x naught plus TA. Well, if A had equals 0 here, that would go over to 0. We would just get x is equal to x naught. And our equation here would just be different. You would just have x is equal to x naught and then these two being equivalent. So you can alter these equations given various values for A, B, and C that way. Okay, so let's do an example here. Find parametric and symmetric equations for the line L given by for the line L passing through the points, I'm going to say passing through, and this chalk is running out of energy. No, this one here. 2, 4, -3, and 3, -1, 1. Okay. So notice that we can take this as our initial point, P naught, and we can take this as our point P. Just like how we highlighted it in our diagram there. We had R naught, we had R, this was P naught, this was P. We then construct this to be VT, okay? And so the vector equation for the line is R is equal to R naught plus a V T, okay? So we need to find what R is, or R naught is. R naught is really the displacement vector of these two positions, the origin and P naught. If it's the displacement vector of the origin and P naught, we should know by now through our studies that that must equal that. Okay? Now, all that's left to determine is what V is, and then we scale it by some T. Notice that VT is the displacement vector here. Simple as that. And so we get that when we take the displacement vector of these components, we get final, which is 3, minus initial, which is 2. Final, which is -1, minus initial, which is 4. Final, which is 1, minus initial, which is -3. So I get 1, -5. These add, so I get a 4 here. Okay. So now, notice I said that this was VT. Really, what we wanted to say was, remember we said that this was V, and this was really A. A was defined as this guy, and that we needed to find some scalar such that V times T would equal A. So that means actually this really is technically equal to our A. So it's really the same. It's just the same thing. What we're saying is the same thing. Multiple ways of saying the same thing here. So from this equation, because R is equal to this, and that should equal our R naught, which we've calculated, is 2, 4, -3, plus, you know, this equation was also equal to that. So that means this right here, if I want to convert A, I must replace it with a VT, but V has the same values here, just scaled by a T. Okay, so I scale this vector A by a T. T, 1 minus a 5, 4. And I do the computation here. I do vector component addition. Distributing the T and adding, I get 2 plus a T. I get 4 minus a 5T. And I get -3 plus a 4T. Any questions so far? We're just adding the components, right? X component added to Y component. And over here, I distributed the T to each term, and then we added them. So remember, this was always equal to this. And so I can set X equal to this component. I can set Y equal to this component. I can set Z equal to the third component. Boom. This is the parametric equation for the line utilizing the parameter T. All right. We can eliminate the parameter T as well. Notice what happens when we do that. I get T is equal to X minus 2. I get T is equal to 4 minus a Y divided by -5. Right. And I get T is equal to -3 minus a Z all over 4. Or that seems wrong. I should get Z plus 3, Z plus 3 divided by 4. That's what should we get there? There we go. Add a 3 divided by 4. Subtract the 4 divided by -5. Okay. So actually, this should say -4. Subtract the 4 divided by -5. And T, that one's good. Okay. Any comments or questions? Does it look right?
On the middle one, wouldn't it be -4 plus y?
So here's the thing. Here's our equation. I subtract the 4. So yeah, it should be positive. Yeah, it should be y minus a 4. So I had it right. Y minus a 4 divided by negative 5. Thank you. I need to sleep more. Okay. So then you could just set each of these equal to each other because t is equal to t, which is equal to t. So x minus 2 is equal to negative 4 plus y divided by negative 5, which is the same thing as 3 plus a z divided by 4. They're all the same. So then we've eliminated the parameter t. Because we wanted to find the equation for the line, so we found the parametric equation, and then it said also find the symmetric equation. So the symmetric equation is whenever you eliminate the parameter t, we get the symmetric equation. This is the parametric equation for p, and this is the symmetric equation for s. So here's a question. At what point does the line intersect the xy plane? To answer this, we must think about what are each of the values for the x and the y and the z in the xy plane. One of them, either it's x or it's z or it's y, has value 0, right? Because if you're in the xy plane, then you're restricted to motion in only the x and only the y, not the z. So what is your z set equal to? Very good. It's set equal to 0. So when does L intersect the xy plane is equivalent to getting this set of equations and setting z equal to 0. Okay. So for when z is equal to 0, this implies that this top part, this becomes 3/4, right? So I get 3 over 4, which is equal to 4 plus y divided by negative 5. And I get 3 over 4 simultaneously is equal to x minus 2. And again, I'm messing it up here because this needs to be a negative on this 4. Woo! Okay, so you just solve for x and y respectively to find that point in which it intersects the xy plane. Notice that here, x is equal to 3 over 4 plus a 2. So that's 3 over 4 plus a 8 over 4, because I multiplied top and bottom by 4. And so x is equal to 11 over 4. That's the x component that intersects the xy plane, the x-intercept, if you will. And over here, then I get negative 5 times 3 over 4, and I add a 4, equal to the y component. So then this equals negative 15 over 4 plus 4. So this equals negative 15 plus 16, everything over 4. So that's equal to 1/4. So we killed that question. We found where does this line intersect the xy plane. When we hear xy plane, in our heads we know, oh, that is the set of points in R3 such that x can be anything, y can be anything, but z is restricted to 0. Because of that fact, we can solve this. And that's why the symmetric equation representation is powerful. But I would say the parametric representation is more powerful because with that, you can derive the symmetric. So we care very much what comes first, the chicken or the egg in math. We care very much. What came first, the chicken or the egg? That's a silly question. A very silly question. But I always found that question funny. Now, in general, let's generalize this notion again, even further. If P naught is equal to X naught, Y naught, Z naught, and P is equal to, or let's call it P1 is equal to X1, Y1, Z1, I won't draw that diagram out again. The one with the vector R naught, R, A, V, VT being equal to A. Okay, all that stuff, once you apply it to this new relabeling, this gives us the following. X minus X naught divided by X1 minus X naught. That would be a symmetric equation. Y minus Y naught divided by Y1 minus Y naught. Another symmetric equation. Z minus Z naught divided by Z1 minus Z naught. Okay. We can derive these equations here. So this right here is what we did in this problem that we just solved. It's just we didn't know we were doing it. But this is the general procedure. Really, you don't even need to know this. All you need to do is know that the vector equation for a line is R is equal to R naught plus A. Change that to VT, use vector addition, set components equal to each other, and you should be able to derive that from that each time. I like to start from the scratch. Okay. Here's another thing we can do. We can talk about not only just arbitrary lines, which extend infinitely, right? But we can also talk about a line segment between them. If this is some point A, this is some point B, how can I describe the line segment? Okay, let's say A is equal to 2, 4, negative 3. And let's say B is equal to 3, negative 1, 1. Okay. Notice that doing this process, we can derive that X is equal to 2 plus T, Y is equal to 4 minus 5T, Z is equal to negative 3 plus a 4T. Okay. So, notice that to describe only the line segment from here to here, we can just pick values for the parameter T, and it will land us in these spots here. Notice that when I pick T is equal to 0, we'll land in this spot, because then I would get 2, 4, negative 3. Yeah, I love the head nod. I'm happy to see that. You're following me. That's beautiful. Notice when T is equal to 1, we land here, because 2 plus 1 is 3, 4 minus 5 is negative 1, 4 plus a negative 3 is a positive 1. So you see that? So we can say that this line segment from A to B, A to B, I don't know how you talk about line segments. I don't know, is there a line on top of it? I'm not sure. I don't know what notation is the best. But you can say that it equals this vector equation, R of T, right here. 2 plus a T, 4 minus a 5 T, negative 3 plus a 4T. And to describe this segment alone, you can just say, okay, I want to let T vary between 0 and 1 inclusive. So now we can describe line segments by restricting the parameter. We should restrict the parameter T between 0 and 1. And then it ranges from here to here. If we don't restrict the parameter, then we're talking about the whole infinite line. The line that is going to infinity in both directions. So here's another formulation. If you do that diagram, I'm not going to draw it, but if you do the diagram, you can re-represent V as the difference between R and R1, okay? Where remember, P naught was X naught, Y naught, Z naught. P1 was X1, Y1, Z1. And so R naught is a displacement vector from the origin to P naught. And R1 is a displacement vector from the origin to P1. Notice that V is equivalent to subtracting them. It's like the difference between them. So notice that if V is equal to this, that implies in our vector equation for a line, R of T, I get R naught minus A. This was what it was originally. But notice that we converted that to R naught minus a T B. And notice that, again, we're converting that to an R naught minus a T times this entity. Okay. So then notice we can distribute the T and combine like terms. So I get R naught minus a T R naught plus a T R1. And I can factor out an R naught here. So I get R naught, which is a vector, is 1 minus T quantity plus a T R1. This is another representation of our, this is another vector representation of our line. Okay. But now we're using the points P1 and P naught and P1. This is the representation between 2 points. So let's do an example here. Show L1, which is equal to notice that technically L1 is a vector, isn't it? So we can do that, or and then L2, this is equal to, oh man, I hate this notation. So 2s, but I'm just going to put a line through it to not confuse it with 5s. 3 plus s. Okay, I'm going to put a line through it to not confuse it with 5s. So show that line 1 and line 2 are skew. Skew. Who here knows what skew lines are? Do you guys know what skew lines are? No? Okay. So usually in 2 dimensions, 2 lines were either parallel or perpendicular, or they just intersect at a non-right angle, right? Those are the 3 options. If you have 2 lines in a plane, they're either parallel or perpendicular, or they intersect at some non-right angle, right? But notice that this is just in 2 dimensions. If we expand in 3 dimensions, there's this possibility. So this line can be traveling infinitely through here. This line can be traveling infinitely through here. And they'll never touch. Okay, so two lines are skew if they do not intersect and are not parallel. Because if they were parallel and there was a space between them, then you could just say that they're parallel. Just like in 2 dimensions, we could have said that they were parallel. In 3 dimensions, we can say that they're parallel. So they must not intersect and not be parallel. So how can we determine what is the angle between these two lines? What is a tool that we've developed that would allow us to determine what is the angle between two vectors? That's right. The dot product. Notice that this is equal to this. Right? And if that were to equal, let's say 0, we would know that they're perpendicular. That's one way to go about it. Another way to go about it is to determine whether one is a scalar multiple of another one. Okay? I'm telling you all the tools you have that you can study the angles between two vectors. There's dot product you can use. Then you could talk about, is one a scalar multiple of another one? So if they're parallel, one's a scalar multiple of the other one because here's the original, scale it, it's a graph transformation. Original, scale it, and it doesn't matter if I move it into 3 dimensions either. Okay, so another way to determine it is to see whether these guys are scalar multiples of each other. So that is an easier way to do it because using this right here would only tell us what the angle is between them. And it can be done if you chose values for t and s. But another way to do it is choose values for t and s and see if one is a scalar multiple of another one. So I like to pick t equals 0 and s is equal to 0 because that makes my life easier. And this becomes 1, -2, 4. That's what L becomes. What does L1 becomes? What does L2 become? It becomes a 0, a 3, -3. Right away we realize there's no number I can pick here to multiply through each of these components for it to turn to these numbers. Because notice that no number, there does not exist a number that we can multiply times 0 to make it equal 1, right? Because there is no number that we can multiply times 0 for it to equal 1, then L1 and L2 cannot be scalar multiples of each other. We're wanting to see, does there exist some like x? Does there exist a x in a real number such that x L2 would equal L1? And the answer is no. There does not exist an x, a real number, such that if I multiplied x times these component values, that it would change it into these components. No number times 0 will give you a non-zero value. So we know that they are not parallel. Because if they were parallel, then there would exist an x that would allow you to do this. Okay? If they were to be parallel, there would exist an x to let you do this. A real number that will allow you to scale it. but there isn't. So now all we got to do is see if they intersect or not. Well, how will we do that? Well, we see, is there a T and an S that allow this component to equal this component, and that component to equal that component, and that component to equal that component? Does there equal a T or an S that allows them to have the same value? Because that means they're intersecting. So let's try it. We set each of the components equal to each other. All right. Now we solve a system of linear equations. 3 equations, 3 unknowns. Okay. Notice that solving for t, I get in the first equation, I get t is equal to 2s minus 1. Using the method of substitution, plugging that into this equation, I get negative 2 plus 3 times 2s minus 1 should equal 3 plus s. So I get negative 2 plus 6s minus 3 is equal to 3 plus s. Okay? So these combine to give me a negative 5, and when I add them over, that's 5 plus 3, which is 8. So bringing the calculation over here, I have this equals 8. And when I subtract an s, I get this equals 5s. And so s should equal 8 over 5. Right? 6, negative 3, yes. So those combine. Yeah, that looks good. So if that's the case, then I can plug back s into this equation to find what t is. T would equal 2 times this 8 over 5 minus a 1. So then it equals 16 over 5 minus a 1. So then it equals 16 minus 5 all over 5, which is equal to 11 all over 5. That's what our supposed t equals. And this is what our supposed s equals. Okay? So they intersect, right? Because we found t and s. Not necessarily. We have to see whether this t or this s, when we plug it back into the equation, solves the equation appropriately, right? So let's plug in t and s and see if the left-hand side equals the right-hand side. 4 minus my t, which is 11 over 5. Does that equal my 3, or my negative 3 plus my 4 times this s? 8 over 5. They should equal, right? If they don't equal, that means there's a contradiction, and that means that they don't intersect. Let's see. So giving a common denominator, I get 20 minus 11 all over 5 here. This should equal negative 3 plus 32 over 5. Okay? Automatically, I see that this isn't going to work, because this is going to equal to 9 over 5. And this is going to equal negative 15 plus a 32 all over 5. But what is 32 minus 15? 17? So this is 17 over 5. Does 17 over 5 equal 9 over 5? No, it does not. So that's a contradiction. When we solve for t and s, and we plug it back into one of the equations, it should give left-hand side equals right-hand side. Left-hand side equals right-hand side. Left-hand side equals right-hand side. For all of them, it should work. And it doesn't work. We only had to check one to see that it didn't work. So that means there does not exist an s, and there does not exist a t, such that this component will equal that component, this component will equal that component, and this component will equal that component simultaneously. Meaning they never intersect. Meaning they're not parallel and they don't intersect, so they're what? They're skew. Moving on to planes. Now Calc 3 is getting really fun. The pictures in your book are going to start getting really cool. Planes. Okay. So to describe a line in 3 dimensions, we needed a point and a vector giving a direction that's parallel to that line. Now, notice that that's not a sufficient amount of information for a plane, because given the plane, let me say I have a point on it. Let me say I have a vector pointing somewhere. Okay, how do I know how to draw the plane? How do I know if the vector points this way or this way, perpendicular to it, or downwards or this way? I don't know. I need to know because the plane is flat. And so the vector being perpendicular to it doesn't work, right? And the vector pointing down doesn't work. The vector pointing to the side doesn't work. So that's not sufficient enough information. So to find sufficient enough information, you don't need a point and a vector that is parallel to the plane. You need a point and a vector that is perpendicular to the plane. Yeah. So before we said that this wouldn't work. The vector is on the plane. So now we're going to need some vector that's perpendicular to the plane. We call this vector the normal vector. Why does this end up working and the other ones don't? Well, it's because we can say that at any point on this plane, I can define this normal vector. And, you know, if n is here, then Tn would be over here. It's just a scaled version of it. So at any point on the plane, I can define the normal vector. Then I can define the set of elements in R3 that are part of this plane. Okay. So do a quick derivation here. So we got our vector R here at this point. We've got some vector R naught here at this point. This is P naught equaling X naught, Y naught, Z naught. This is P equaling X, or are we calling it P1 here? No, we're calling it P. Calling X, Y, and Z. Then we can create a vector between these 2 points. It's going to be the displacement vector between P and P naught. Okay? And actually, that displacement vector between P and P naught is the same thing as taking R minus R naught, because of vector addition. If you imagine putting them in head to tail fashion. I can't draw it well, but if you put these guys head to tail fashion, you'll get. So that's why it's not working. Well, you'd have to reverse this in direction, so this would have to point this way, head to tail, and you should get a resulting vector looking like that. I'm trying to make it happen quick, and it's not working. But at that point over here at P1, we can define our normal vector n. So let me write down in equations what I've been saying out loud. I said r minus r naught is a displacement vector between P and P naught. Okay. Then we notice that if we construct this vector n that is perpendicular to this plane, what must be true about the dot product between this vector n and r minus r naught? What is the angle between r minus r naught and n? 90 degrees. Right. Because this dot product means magnitude of n, magnitude of r minus r naught, cosine of theta. Cosine of 90 is 0. So this whole equation is equal to 0. Then we use the dot product axioms to distribute that dot product, n dot r minus n dot r naught. We set that equal to 0. And then we derive our final equation. You could stop here, or you can go to here one step further. Put a knot there. So this is the vector equation of a plane. And so is this. They're both the vector equation of a plane. Both these guys are the vector equations of the plane. Okay. Notice that we can also have a scalar equation of the plane. Okay. So if we let n have values a, b, c, and we know r is equal to x, y, z, and we know r naught is equal to x naught, y naught, z naught, this equation right here states that n dot r, which is equal to ax plus by plus cz, should be equal to n dot r naught, which is equal to ax naught plus by naught plus cz naught. They're equal. So when I get everything on one side and factor out a, b, and a c from each term, the equation becomes a x minus x naught plus b y minus y naught plus c z minus z naught. And you know, we got them all to one side, so that means that everything will be set equal to 0. Because these guys used to be hanging out on one side, we brought them all the way to here, factor out of a, factor out of b, factor out of c, and we get this. So this becomes our scalar equation of a plane. So over here, this was a vector representation because it has vectors in the expression. But in reality, because we're taking dot products between two vectors, it was always really a scalar equation for a plane. So we still have some stuff to cover in this section, but we're mostly through it. So I'll assign the homework for it. Okay. The other, was it, when did I assign the homework for 9.4? It was on Friday, wasn't it? No?
It was on Monday.
It was on Monday? Okay. This Monday?
Yeah. So
Okay.
due-
So it's due next Monday. Got you. Thank you so much. I have a poor sense of time. Yep. If you guys don't have any questions, then I'll see you guys later. Feel free to email me any questions that you have as well.
I did have one real quick.